Hi students, welcome to our second and last video in our second set of videos about Lewis structures. We're almost there, keep studying. This lecture, or this video, is about syzygies. So this can be a very hard concept for students to grasp, especially for many it's their first time seeing it. So we're going to walk you through an example molecule, or ion in this case, of SiF5Cl2-. So here on the very left side, you can see another handy checklist that we'll be using to draw our Lewis structures. It's the same one that we've been using. So the first thing that we do is we identify our central atom. So within SiF5Cl2-, silicon is our most electropositive atom, and so that will be our central. Our second step here is to calculate our steric number. And so if you recall, the steric number formula is written right above there, and so in this case we have 4 contributing electrons from our central atom, and then we have 5 from our fluorines, and then we have 1 from our chlorine, and all of this is divided by 2. Oops, my mistake. We also have a charge, and this is our first time seeing that, so we have to add 2. And so all of this is over 2, and it gives us a steric number of 6. Our next step is to connect all of our atoms within a single bond once we've identified what shape we have. And so if we go back, we have our chart here, and so we can see that a steric number of 6 with a parent structure, given that we have 6 peripheral atoms, would be octahedral. So let's place our atoms around the octahedral framework now, and so we have our silicon in the center, and then our fluorines and chlorines as peripheral atoms just around. So we would connect all of these with a single bond for now. Remember to use your wedges and dashes. Okay. So now we need to fulfill our octet rule for our central atom. So as it is right now, our central atom silicon has 6 bonds to it, which means that it has 12 electrons. That's 4 too many, and so we need to remove some bonds. So this is where the concept of syzygy comes in. So a syzygy is a 3-center, 4-electron bond, or in other words, it looks like 3 atoms that are in a straight line with each other. So in this case, we can see that in our currently drawn molecule, we have 3 different syzygies that could happen. So we have that one that's very vertical, our fluorine, silicon, and chlorine. We have the 2 diagonal ones with fluorine, silicon, fluorine, and fluorine, silicon, fluorine. And so in this situation, if we're deciding which bonds that we'd like to break, we should look at first electronegativity, and second, consideration that we cannot remove bonds from the same syzygy. So in this case, given that we're removing 2, we would remove those from anything but the chlorine. So let's redraw our molecule in just a second. So here we can see that we removed our bond to the fluorine above and then a random fluorine from any of the other 2 syzygies. So let's redraw our ion with our final bonds. Okay, great. So now our central atom silicon has 8 electrons around it, and so we have fulfilled its octet rule. Next, we need to fulfill our octet rule for our peripheral atoms. So let's go ahead and fill those in. We need to add 8 around those isolated fluorines, and then 6 around each of our non-isolated fluorine and chlorine. Great. So now don't stop here. We still need to get to formal charge. And so our next step is we need to calculate those. So here we have a chart that shows you the number of bonds corresponding with formal charge equals 0 and obeying an octet rule. And so in this case here, we can see that the fluorine, the ones that are isolated, have 0 bonds. And so they kind of look like neon's octet would. And so in this case, we can say that in order for fluorine to look like neon in this case, it must have gained an electron, and so therefore in this case, it's -1. This is almost a shorthand as opposed to using the formula that we gave you all earlier. So those other fluorines and the chlorine there, we can see have 1 bond. So in that case, we can see them in that second from the right column. So they have both their octet rule obeyed and their formal charges equal 0. So none of them have a formal charge. For the silicon, we can see that it started with 4 valence electrons and it's now ending with 4. And so same thing, we can see it has the number of bonds as 4, and so it has a formal charge of 0 as well. Okay, back to our checklist here. We just need to do a final check now, and so we can see that we have our sum of our formal charges as -2, and our ion had started with a charge of -2, and so in this case, we are all done. We know that we have a correct structure.